Welcome back, everyone. Ready for another deep dive?
Absolutely. Always ready to jump into some cutting-edge science.
Well, today we're going to be talking about particle acceleration.
Oh, wow. Particle acceleration.
Yeah. Specifically, we're going to be looking at some research from the Berkeley Lab Laser Accelerator Center, Bella,
Okay.
based on their findings published in Physical Review Letters.
Sounds fascinating.
Yeah, so get this. They figured out how to accelerate electrons to incredibly high energy levels, and they're doing it with lasers and gas.
Really?
Yeah, essentially they're shrinking the size and cost of particle accelerators, like dramatically.
I mean, that has such huge implications for so many different fields. We're talking revolutionizing cancer treatment, potentially unlocking secrets of ancient civilizations, even, pushing the boundaries of high-energy physics research.
That's right. So this research focuses on something called laser plasma acceleration.
Okay.
And it might sound complicated, but think of it this way. Imagine electrons. You know those tiny particles? Imagine them surfing on powerful waves created by lasers.
Okay.
And these waves exist in a superheated gas called plasma.
Gotcha.
So as these electrons are riding these waves, they're picking up an incredible amount of energy.
That's a great analogy. So how much energy are we talking about?
Well, the team at Bella has successfully accelerated electrons to 10 GeV.
10G, wow.
That's 10 billion electron volts, which I know sounds like a lot.
It does.
And it is. And they're doing this in a distance of just 30 centimeters.
30 centimeters, that's shorter than a ruler. To get these kind of energy levels, don't traditional particle accelerators like the Large Hadron Collider, those need kilometers, right?
Exactly. I mean, you think about the Large Hadron Collider. That's massive.
Yeah.
This is 30 centimeters. I mean, that just shows how significant this is.
Yeah, it's really, really remarkable.
Now, I was reading through the article, and they mentioned using a dual laser system. What's the advantage of that?
Right. So the dual laser system is really key here. It's like a carefully choreographed dance, okay? So you have the first laser. This acts as like a drill.
Okay.
And it creates a channel through the plasma. And then the second laser, this is even more powerful laser, acts as like the driver.
I see.
Accelerating the electrons within that channel. So it's kind of like creating a superhighway for these electrons to race down. It allows for much greater control and precision.
So it's not just about brute force. There's a lot of finesse involved as well.
Exactly. It's a very carefully controlled process.
Now, one thing that stood out to me, they've moved away from using those fixed-length glass tubes, the capillaries,
Right.
to shape the plasma. Instead, they're using supersonic gas jets. So why make that switch?
Yeah. So it's all about flexibility and control. You see, those capillaries, they're like trying to fit a square peg in a round hole. This new gas jet system is so much more adaptable. And this is huge because it allows the researchers to fine-tune the properties of the plasma, the density, the length, even the shape. They're essentially sculpting the ideal environment for electron acceleration.
So they're able to optimize the process in ways they couldn't before.
Exactly. And, what I find really, really cool is that this new approach, it offers greater visibility into the acceleration process itself.
So before, it was kind of like operating in a black box. You could see what went in and what came out, but you didn't really know what was happening in between.
Right, exactly. But now with this gas jet system, they have a window into every stage of the process. They can see how the laser pulse is evolving, how the plasma wave forms and propagates, how the electrons are trapped and accelerated.
So it's not just about achieving higher energies. It's about gaining a much deeper understanding of what's actually happening at a fundamental level.
Absolutely. And this deeper understanding is so crucial for, refining our models, identifying potential challenges, and really pushing the boundaries of what's possible with laser plasma acceleration.
Now, they also mentioned eliminating something called dark current. Can you explain what that is?
Yeah. So imagine you're trying to send like a focused beam of light through a really foggy environment. What happens? The fog scatters the light, right? Makes it weaker, less precise. Well, dark current is kind of like that fog. It's caused by unintended acceleration of background electrons, and it saps energy from the main electron beam. It makes the whole process less efficient. What's remarkable about this new setup at Bella is that they virtually eliminated this problem.
So they're clearing away the fog, if you will,
Yeah.
making the whole acceleration process much more efficient and powerful.
Exactly.
Now, I'm just thinking about all the factors involved here. It's pretty complex, and I imagine it takes a lot of computing power to model these interactions.
You're right, this level of precision wouldn't be possible without some pretty serious computational tools. The researchers rely on sophisticated computer simulations to model these interactions. One of the key tools they use is a code called INFRNO.
INFRNO. Yeah, I've heard of
Yeah.
that. That's a pretty hardcore piece of software.
Yeah, it runs on supercomputers, allowing them to virtually test their theories and validate their experimental findings. It factors in just a huge number of variables: the shape of the laser pulse, the density of the plasma, even the magnetic fields generated during the acceleration process. It's like having a virtual laboratory.
It really is amazing to think that we can model these really intricate high-energy processes with such accuracy. So we've talked about how it works, but what about the real-world applications? Where could all of this lead?
Well, that's where things get even more interesting. That's what we'll dive into next. The possibilities are really mind-boggling. I mean, we could revolutionize medical treatments, explore the mysteries of the universe. Really, it's incredible.
I'm excited to hear more. We'll be right back after a short break.
So we were talking about the potential applications. I mean, where do we even begin?
I know, right? You mentioned revolutionizing medical treatments. I'd love to hear more about that. What kind of impact could laser plasma acceleration have on healthcare?
Well, one of the most promising areas is in cancer treatment. Imagine, like, compact, affordable particle accelerators that could be used to deliver targeted radiation therapy.
Right, in a local clinic.
Yeah, exactly. And that could, really democratize access to these life-saving treatments for so many people.
That's incredible. I mean, especially for people in areas with limited access to specialized medical facilities, that would be a game changer.
Absolutely. And beyond cancer treatment, there's exciting possibilities in medical imaging and diagnostics,
Okay.
more precise imaging techniques, earlier disease detection. I mean, it's really remarkable.
So this technology has the potential to transform healthcare on multiple levels.
Oh, absolutely.
Now, earlier you also mentioned unlocking secrets. What did you mean by that?
Ah, yes. So one of the most, I'd say, captivating applications involves using laser plasma acceleration to create muon beams.
Ion beams.
Yeah, so muons are these subatomic particles, and they can penetrate deep into materials without causing damage,
Okay.
which makes them perfect for non-invasive imaging.
So it's like having X-ray vision, but on a whole new level.
Right. I mean, think about it. Ancient pyramids.
Oh, wow.
We could create three-dimensional images of the interior without ever having to excavate them.
That's amazing. You could uncover hidden chambers, map out complex tunnels. We could even find lost artifacts.
Exactly. It would revolutionize archaeology. And, that's just one example.
Yeah, what about other applications?
Well, you could use them to, map the internal structure of volcanoes, help predict eruptions, mitigate risks, or inspect bridges and dams, nuclear reactors.
So it's not just about uncovering the mysteries of the past, it's also about safeguarding our future.
Yeah, very much so.
We've talked about healthcare, archaeology. What about material science?
Oh, well, laser plasma acceleration could power a new generation of free electron lasers,
Oh, okay.
which are essentially extremely powerful microscopes.
So we're talking about probing matter at the atomic level, developing new materials with properties we can barely imagine.
Yeah, exactly. Stronger, lighter materials for aerospace, more efficient solar cells. I mean, it could unlock a materials revolution.
And this could have huge implications for industries from transportation to energy to manufacturing.
Exactly. We've talked about healthcare, archaeology, material science, but we can't forget about high-energy physics research. I mean, that's where it gets really exciting in terms of, pushing the boundaries of our understanding of the universe.
Right, because traditional particle accelerators they're reaching their limits in terms of size and cost.
Exactly.
But laser plasma acceleration, this could be a more compact and affordable way to achieve those really high energies needed to study the fundamental building blocks of matter.
Right. I mean, essentially, we're talking about building the next generation of particle colliders.
So, smashing particles together at incredible speeds, studying the debris.
Yeah, with the goal of understanding those fundamental forces that govern the universe.
And with laser plasma acceleration, we could potentially build, tabletop colliders that achieve energies similar to the Large Hadron Collider.
Yeah. I mean, imagine discovering new particles, new forces, maybe even new dimensions. It's pretty mind-boggling to think about the potential discoveries.
It really is. But let's be realistic for a moment. We've talked about all this potential, but what are some of the challenges in developing and implementing this technology?
Well, one of the key challenges is scaling up those energy levels. while also maintaining the stability and the quality of the electron beam. It gets more and more complex as we push toward those higher energies.
So it's kind of like trying to tame a wild beast.
That's a great way to put it. And, it's not just about the energy, it's also about the beam quality. For a lot of applications, you need a tightly focused, stable beam, and maintaining that quality at higher energies, it's tough.
So there's still work to be done.
Oh, definitely. Another challenge is developing systems that are robust and reliable. These laser plasma accelerators, they're still relatively new. So ensuring their long-term stability and performance is really crucial for any real-world applications.
It's one thing to prove in the lab, but it's another to make it work consistently out in the world.
Right, exactly. And, we talked about INF and RNO. Simulations are really powerful, but they're only as good as our understanding of the physics behind them. So as we push towards those higher energies, our models need to become more sophisticated to really capture what's going on.
So there's this constant back and forth between the experiments and the simulations.
Right. The experiments give us data that helps us improve the simulations, which then guide the design of new experiments.
So it's really a collaborative effort.
Oh, absolutely. It's like this amazing collaboration between experimentalists, theorists, physicists, computer scientists.
It's fascinating to see all these different fields coming together to push the boundaries. And, despite the challenges, the progress that's been made in laser plasma acceleration it's really remarkable. I mean, we've gone from a theoretical concept to demonstrating record-breaking energy levels.
And all in just a few decades. It's a testament to the ingenuity and dedication of the researchers working in this field. And, it's exciting to think about what the future holds as we continue to unlock the potential of this revolutionary technology.
It really is. Now, before we get too carried away with those future possibilities, let's take a moment to appreciate what's been achieved here. What are the key takeaways from this particular breakthrough? Why is it so noteworthy?
Well, this research, it really represents a major leap forward. Not only have they achieved these record-breaking energy levels, but they've also demonstrated incredible control over the entire process. I mean, it's really paving the way for a whole new generation of particle accelerators.
Particle accelerators that are compact, powerful, and versatile. It's a good reminder that sometimes the most groundbreaking discoveries come from challenging the status quo.
Right?
I mean, who would have thought we could accelerate particles to such high energies using lasers and gas?
I know, it's credible, and it really underscores the power of scientific curiosity.
Yes.
Pushing the boundaries of what we think is possible. It's amazing to think what this could lead to.
It really is. And I think one of the big takeaways here is just how many potential applications there are. This could impact so many different fields.
Oh, absolutely. Healthcare, energy, materials science, fundamental physics research. I mean, the list goes on.
And it's not just about making things a little bit better. We're talking about potentially changing things completely.
Right. Laser plasma acceleration could completely disrupt the way things were done now, open up completely new possibilities.
When we were talking about muon beams earlier,
Yeah.
it really struck me how this technology could change the way we see the world, literally.
I know what you mean. The idea of looking inside things without damaging them, I mean, it's incredible.
Whether it's a pyramid or a volcano or even the human brain, it opens up so many possibilities.
It's like we're gaining a new set of eyes.
Exactly.
A way to see things we never could before. And it's not just about seeing, it's about understanding.
Right.
I mean, with laser plasma acceleration, we could understand the universe in a whole new way.
So we've talked about the challenges.
Yeah.
But what about the timeline? How long until we actually start seeing these applications?
That's a tough question. It's always hard to predict when these kinds of breakthroughs will happen. But, I mean, the progress in laser plasma acceleration has been amazing.
Yeah, in just a few decades, we've gone from theory to reality.
And I think it's safe to say we're moving beyond science fiction here.
It seems like it.
Some applications, like those compact particle colliders, those might be a while off, maybe a few decades.
Okay.
But other things, like medical imaging and material science, we could see those a lot sooner.
So it's an exciting time to be watching this field develop.
It really is. It feels like we're on the verge of something huge.
It's like we're watching a scientific revolution unfold.
And it shows how important it is to support basic research, because you never know what those discoveries might lead to.
That's right. In this case, it could revolutionize multiple fields. And that's pretty incredible.
It is.
Well, I think we've given our listeners a lot to think about. It's been a fascinating deep dive into the world of laser plasma acceleration.
It has. It's been a pleasure talking about this with you.
Likewise. And everyone listening, stay curious, keep exploring, And who knows, maybe you'll be the one making the next big breakthrough. And that's it for this deep dive. We hope you enjoyed it. Until next time, keep exploring the world around you. There's always something new to discover.